Hi everyone. I would like to start the second part about how you can use Redis as your primary database. And today we start with talking what's new with the active-active geo-distributed Redis, which we call Redis CRDT. So you may ask yourself, why do I need active-active? So there are multiple use cases. One of them is probably the simple one. You have a session store, you put everything in Redis, and you deploy your data center across, you deploy your application across multiple data centers. You want to make sure that when your users switch by the DNS from one data center to another, you still have the states, you still have the context. This is one example. The other example is if you want to develop more advanced applications that simultaneously read and write to the same data set for multiple locations. Now, the problem that if you try existing technologies like DynamoDB and Cassandra, which relies on eventual consistency mechanism, you need, every time you read or write, to wait for the majority of the replica to get your updates. That means 100 millisecond latency, or in other words, 10 updates a second for each connection, which is, of course, very, very low number. In addition to that, if you try to do it in a fully consistent manner, strong consistent manner, like there is in Spanner, you need to wait for all the replica to get your updates. So in average use case, you will get something like 200 milliseconds for the response time. This is a big problem for all the modern applications today. The other problem with this type of configuration is how you do the conflict. Once you write from different locations, how you do the conflict resolution. If you try to do it at the application layer, this is going to be a very hard task for you to develop. And if you use traditional mechanism like class try to win, this is good for simple use cases. But if you look at the complex use cases of Redis, in most cases, you will lose your entire data, your entire keys, or whatever. And you probably heard about the technology that is called CRDT. It stands for Conflict-Free Replicated Data Types. It was invented by a group of professors about 10 years ago to solve this problem. CRDT tries and solves problems like conflict resolution of complex data types as well as simple data types. And in addition to that, it allows you to run like your database is a local database, not across the one, and to get the speed of a local database. And what we did with Redis CRDTs, we implemented everything that this technology provides on the top of Redis data types. Let me show you how it works. So you have deployed your application across multiple geo-regions. Each application looks at the Redis like if it were a local database. Behind the scene, there is no consensus protocol. It's called consensus-free. We just send updates. And every replica converged to the same value by using the same internal mechanism. This is called strong eventual consistency, because you don't need consensus protocol in order to get to the same value, to the same converged value. And this allows you to run over one infrastructure with sub-millisecond latency. The beauty of CRDT is that the conflict resolution, we do different conflict resolution for each data type of Redis. So for the simple use case like string, we use last write win. But for counters, we choose a different approach. We actually don't need to do anything. Someone adds something, the other one reduce something, and we just do the converge by summarizing everything together. Let me go through a simple example. Let's assume we have replica A and replica B. Replica A writes to key 1 the word Redis. And then there is a synchronization between the two. So if I get the value of key1, it will be in replica A and replica B. And now there is a concurrent operation. When we say concurrent operation, we don't mean that it happens at the exact same time. It happens in a case in which the replicas, they don't know the state of each other. In this case, replica B appends wins and replica A decided to delete the key. And once there is a sync between the two, CRDT choose adds wins. Redis always wins, yeah? And this is the value that you get eventually. But it's important to understand that if you look at the time, the concurrent operation didn't happen at the exact same time. It happened in a case where the replicas didn't know about the change that each other is doing. Okay? Now, we started CRDT, we announced CRDT about a year ago, and I would like to go through the stages that we did, through the implementations that we did in order to make this product available. The GA of the product happened late 2017, and we supported in the initial version set, hashes, and string, as well as pub/sub, expiries, up to 3 replicas, and compression across the one. Early this year, we released another version of the CRDT's Redis with up to 32 replicas. You can run Redis up to 32 different locations across the world. And you can add and remove replicas as much as you want. In addition to that, we add SSL capabilities to the communication between the replica. And this is a tunable SSL. You can decide whether you want to use it and whether you don't want to use it, and the same connection without changing endpoint, et cetera, et cetera. And today, we would like to introduce a new capability to the CRDT, in which we support the major data types of CRDT, sorted set and list. And for that, I would like to invite to the stage Gian to show you how it works. Gian.
Thanks, Yiftach. Well, hi, everybody. I'd like to show you how easy it is to build geo-distributed applications with Redis CRDTs. I know the acronyms can be scary. But we're going to use a Leaderboard. Leaderboard is a common microservice in many of the gaming apps, creates great gamer engagement. And applications, games, track leaderboards across different games, age groups, difficulty levels of the game, even in different geographies, in zip codes, cities, states, and countries to create that engagement. We're going to have our gamers distributed across US and Europe. And for low latencies, we're going to record our scores in both of those geographies. I'm also going to use the sorted set data type to do this. It's the perfect type for keeping track of it. As the gamer achieves a new score, you can easily record that into a sorted set, and you can easily get the top 10, 20, 100 scores easily for all of these leaderboards. Now, I've got a global database that's set up. I don't believe in fancy UI, so I'm going to take you into the guts of the system. The blue side and the green side represent the US part of our database and the European side of our database. The US users and European users are going to have the local read and write capability at low latencies to record their games and see the leaderboard. So let's take a look at this. Let's record a few scores. So let me start and make sure that there's nothing in there. We're going to start with a couple of scores for user 1 and user 2. Let me just scroll up. So zadd command, I hope many of you know, but this is the easy way to get a score recorded. Alboard 1 is the name of our leaderboard right here, and we're going to pretend that user 1 has a score of 10. Pretty bad, but let's do user 2 with a score of 20. And there's a great command that will actually let you see what's inside the leaderboard. So Alboard 1 is our leaderboard. We're going to see who else is in there. All of the records that we've recorded are there. Now, the great thing is, with the bidirectional replication that Redis CRDTs have, you can see that both sides agree on what the scoreboard looks like. Now, I am going to inject some fault into this, and we're going to use that orange window at the top. So let me partition the network. What I'm going to do is not let these two guys speak to each other. So imagine US and Europe, somebody steps on the cable under the Atlantic and nothing is working. Your UI will tell you that replication is no longer healthy, et cetera. But even though the system is actually experiencing a problem, there's no problem recording locally any more of the user scores. So let's pretend in US there's a user tree. Comes up with a fantastic score, and something around 700,000. And that user actually achieves that score. We record it on his behalf, but Europe is not sitting idle. We've got user 2 progressing in the game. So we're just going to record and update, actually, user 2's score to 999. Now, the interesting thing is, if I take a look at what has happened to the leaderboard, the two geographies no longer agree. What has happened? What happens if we cure this problem? So on one side, user 3 with a high score. On the other side, user 2 has achieved something new and would be pretty upset if he actually didn't keep both of them. So we'll cure the problem. We'll see how the system reacts. But if you're using a regular NoSQL database, the mechanics that Yiftach talked about, which is last writer wins, would pick one side or the other as the winner. So your options are either upsetting user 2 or user 3 and losing one of those achievements. But CRDTs are smarter. With the sorted set, we track the developer's intent, the commands that you've actually run, and smartly merge all of those updates together. So once the problem is cured, if I actually look at what the leaderboard looks like, you will see that in Europe, I can see user 3 and continue to see the user 2's high score. And in US, I do the same. The whole point is, it's extremely simple to build these distributed applications with Redis CRDTs. I appreciate that. Thank you. And with that, I'll hand it back to you.
Thank you.
Thank you.
Jan, very impressive. So in order to further improve the experience and to give the exact same experience like if you were working with a local Redis, we also implemented a very interesting technology which practically means that you can feel locally when you work with Redis, and we call this causal consistency. Causal consistency is a bit complex to explain. I would like to invite Carlos to the stage. Professor Carlos Becerro is a researcher in distributed systems. He's one of the lead researchers for CRDT. So Carlos, welcome to the stage.
So one of the reasons to look at this is that if you look at this example we have just seen, we are only looking at two sides. But as Yiftach has shown us, we can go up to, or Redis can go up to 32 sites. So the communication patterns become much more different. And if you just link the sites with TCP links, what we see globally is source FIFO properties. So I came up with this simple word association game. You can think of it as adding elements to a set. So site A is adding the name Apple, and then that information is propagating to replicate B. And the replicate B will look at that and will try to come up with two words that make sense after seeing Apple. But the problem is that when this information propagates to replicate C, we might see the two words that were added on replicate B, but without the context, without the Apple that was seen locally on B when those words were produced. And this might lead to a bad choice on replicate C that will try to add pitch. And only later on, it will receive the Apple information from there. So we are seeing the updates coming between each pair of sources correctly, but like globally, there is no way to track with this model cause and effect relationships that happen on the system. So in order to address that, one property is causal consistency. Actually, it starts from a very well-known property from group communication from more than 20 years ago, which is reliable causal delivery. So let's look at example with this. And Redis is providing this per key. So now the example makes more sense. So again, the same thing happened on replicate B, and the two words were produced that make sense. But now the system must ensure that Apple is also seen on replicate C together with the other words. So now it's possible for this third replicate to come up with a word that makes much more sense. Good news about this is that you can provide causal consistency without having really to coordinate in a consensus-like way with the other replicas. So this is the kind of the strongest synchronization that you can get while being highly available and partition tolerant. So that concludes. Thank you.
Thank you very much, Carlos. So if we sum up this session, so you have practically 3 choices when you go to active-active deployment. You can choose the Cassandra and the Dynamo way and use eventual consistency with 100 millisecond latency every time you send a request. You can go to Google Spanner or similar technologies and run each request with 200 millisecond latency. Or you can go to Redis CRDT, remains with sub-millisecond latency. Use the strong eventual consistency with causal consistency, which practically provide the same characteristics of strong consistency. This product is available now as software download. You can download it and use it. And it will be soon available on the cloud in a zero-touch model. And there are 2 very interesting sessions today. One at 11 a.m. by Carlos here at this room. You must hear all the theory behind the CRDT. And one at 2 p.m. with Gian, who will present how it actually works with the Redis Enterprise. And this is going to be at MISO. This is the first part. The second part, we would like to introduce a very interesting technology that you all know, which is called Kubernetes. But we use a kind of a different approach to integrate Kubernetes with the Redis Enterprise. And for that, I would like to invite to the stage Uri Shachar, who is the lead cluster at Redis Labs, to describe what exactly we did there. Uri.
Hi, everybody. So, what's double orchestration, dual orchestration? Orchestrators such as OpenShift, Kubernetes, PKS, PCF are, by their very nature, generic. They do an excellent job in managing the life cycle of a really wide variety of different tasks and whatnots. And while they do expose various hook points and APIs, it is very difficult, if not impossible, to have a very fine-grained and customized approach to managing that special Redis process on top of them. And not to mention that when you want to have speed and performance, you want to be able to launch hundreds of databases a second. You want to have sub-10-second failover time. You want to be able to adjust configuration parameters multiple times a second in order to squeeze out that every little bit of resource and still maintain your high performance. And in order to achieve this, we went with a dual orchestration approach, where we have the external orchestrator, again, OpenShift, Kubernetes, PKS, PCF, and the internal orchestrator, which is the Redis Enterprise Cluster Orchestration Layer, working side by side in order to achieve our goals. When doing this sort of double orchestration, you need to be very careful in deciding the boundaries between the 2 orchestration layers, because you really, really, really do not want them to step on each other's toes. And specifically in Kubernetes, but this is also true for the other orchestration layers practically. Kubernetes handles the node auto-healing and node scaling. The Redis Enterprise orchestrator handles shard and database failover and scaling, and shard and database configuration and monitoring. And together, in shared components and via APIs, they handle things like service discovery and upgrade. When running inside a containerized platform, we took the node in a container approach, where we have one pod running multiple services. That's all the Redis Enterprise cluster orchestration, plus Redis shards. And again, that allows us to have our fine-grained level of resource management, dynamic controls on memory, bandwidth, and CPU on the shard level, which again allows us to squeeze out every little bit of resource, and all sorts of performance optimizations, from the little stuff like Unix domain sockets and shared memory into a wide variety of other tips and tricks which we use to shave off that extra tenth of a millisecond that everyone that uses Redis cares about. To recap, so that's the Redis Enterprise on Kubernetes. That's what we use. We have the node in a pod, which I just showed you. We utilize stateful sets, which are the Kubernetes deployment type, which is native for stateful applications. Persistent volumes in order to maintain the Redis backups and to save some of the cluster state, plus a custom controller to handle some of the integration points between the two different orchestration layers. And if we switch over to my laptop and I can make Jian's laptop work, let's just, Jian, how do I? Yes, yes. You can see it's running. This is a simple Helm-based setup. It's really easy, and I encourage you all to try it out. 3-node, 3-pod cluster running on top of GKE, quite easily pushing 1.5 million ops per second, sub-millisecond latency. And that's it for me. Thank you.
Thank you. Thank you. And by the way, Kubernetes with Redis Enterprise is now available, and there is an important session by Vic, who is the product manager at Redis Labs for Kubernetes areas today at 11. Next section, I would like to discuss how Redis on Flash works on the new Intel persistent memory. For those of you who are not familiar with what is Redis on Flash, so the whole idea is that RAM is expensive, and we want to expand the usage of Redis across all the resources of your server. So what we did with Redis on Flash, we split the data set. We put the key and the key overhead of the Redis dictionary in RAM. We always keep it in RAM. And the auth value of your data set are also kept in RAM, but the rest of the value are kept on SSD, local SSD. So this way, we can use much more of the infrastructure in order to run Redis. And in many, many cases, we achieve that by putting almost 80% of your data set on SSD, just 20 in RAM, and achieve similar performance like you use with Redis on RAM technology. So this technology, by the way, doesn't use the local SSD as a persistent layer. In addition to that, you need to continue to have the persistent layer of Redis, which is practically and usually used outside of the node as a network-attached storage. Now, why this is important? So let's take an example of a data set of 2 terabytes with 100,000 ops per second. If you put it on Redis, like using other cloud providers that propose Redis, this will cost you something like $1 million a year. If you put this data with these performance requirements on other NoSQL, it will cost you much less, $750,000 a year, but the latency will be around 10 milliseconds. It's not going to be sub-millisecond like with Redis. On the other end, if you use Redis on Flash, it will cost you only $150,000 a year, and you maintain sub-millisecond latency, like you use with the RAM. Redis on Flash is a mature technology. It's used by many, many customers of us. Everyone who is using it as a primary data store. No more need for other data stores. And all the use cases that you are running are between 0.5 terabyte to 10 terabyte and even more of data set. And this is just a list of some of the users. Some of them are here that are using this for primary data store. Now, interesting stuff. We have been working with Redis on Flash on 3 generations of SSD. For those of you who remember, 2 years ago, most of the SSD came with SATA drives, which is a kind of slow access to SSD. Then NVMe came up. NVMe improved the access to the drive by using PCI Express to access SSD. And in addition, it cuts a lot of layers in the software. So you can see that the performance with Redis on Flash improves dramatically over NVMe. And about a year ago, Intel announced Optane. Optane is practically a new drive, a new SSD drive that uses 3D technology from Intel behind the scene. And as you can see, we run it over few ratio between RAM and Flash. And everything we did with Optane was much more impressive in terms of performance if you compare it to NVMe and to SATA. So as we improve the technology, we get more and more throughput from Redis. Yeah? And today, we would like to share with you what we did with the new generation of persistent memory of Intel. And for that, I would like to invite to the stage Ken Gibson, who is Director of Software Architecture at Intel. Ken, please. Yeah.
Thanks, Yiftach. So I'm excited to be here to talk to the Redis community about this new technology we've created at Intel called 3D Crosspoint. So 3D Crosspoint is a new kind of media that falls between DRAM and NAND flash in the memory to storage hierarchy. So it has this new material has capacity points approaching that of NAND flash, but performance and access latency much closer to DRAM. So it truly fills that gap between memory and storage in this hierarchy. So as Yiftach mentioned, last year, we took the first step to release this technology in the form of PCIe-attached SSDs, brand named Optane SSDs. And so you just saw the dramatic improvement in performance that Redis on Flash can see with this new media running on the fastest SSDs available today. So now we're working on the next step, which is to move that closer to the CPU to create persistent memory based on 3D Crosspoint. So this is really exciting for software developers and especially the in-memory databases like Redis, because now for the first time, you will have multiple terabytes of memory on a standard compute platform that you can access just like memory. So unlike the model that we were all taught, back in our first programming class where you operate on data structures in DRAM, but then to access high capacity, you open a file, you move the data to your high capacity media, you move it back to DRAM to operate on it. Now you can just have multiple terabytes of data structures right there in memory that you can operate on, from your application. So now you can have in-memory databases with truly multiple terabytes right there in memory. So over the last couple of years, to get ready for persistent memory, we've been working with the Linux community on implementing a new feature they call DAX, D-A-X for direct access. So that will be the way that Linux will expose this persistent memory right directly to applications to use as memory. And this afternoon, Andy Rudolph from Intel is giving a talk going into details on DAX in Linux. And so now with that in place, now we're working with the Redis community and with Redis Labs on now taking advantage of that from the Redis application. So with that, Yiftach, I'll pass it back to you to talk about Redis on Flash with persistent memory.
Yes, thank you very much, Ken. So this is how your system is going to look tomorrow. You will have Redis with a tier of DRAM. Part of this will be still DRAM because you want to be smart and keep the very high hot values in DRAM. But the other part, which is a kind of persistent memory or 3D Crosspoint, will be extremely fast if you compare it to SSD. So in SSD, you usually gets latency of something between 20 to 90 microseconds. With 3D Crosspoint, it will be under micro. Yeah? I'm correct, yeah? Now, what is important, when we start working with technology, we didn't see any improvement. It was like, okay, what is all this noise that Intel is doing when practically we don't see any improvement at the Redis level. And now we understood, so what we understood is that you cannot anymore use the same software that you used before in order to access the storage because the overhead of doing multiple tasks, current queuing system and context switching overhead doesn't allow you to utilize the hardware. So as you can see here, before the persistent memory, the way Redis on Flash was constructed, we used the Redis open source, but we created another thread to access the Flash. Yeah? Now, this creates a lot of overhead because there is a context switch, a lot of threads, queue between the main thread, the main Redis processes and the iOS thread. And all this creates a lot of latencies that we cannot utilize the hardware. So what we did in order to improve that, we integrate both the storage engine inside the main memory, and we practically delete the additional threads. Before persistent memory, we use RocksDB, which is a kind of very famous storage engine that I guess many of you are using. But if you look at how RocksDB looks like, it's about 700 lines of codes, over 700 files, over 270,000 lines of code, and it is written in C++. This is a kind of heavy for this technology. So we switch to LMDB, which is only one file, 8,000 lines of codes, and we got much faster performance. But I must say that LMDB is not optimal for 3D Crosspoint. It was written 20 years ago, yeah? And we're still looking to find the right spot, the right infrastructure, the right technology, to access this very high throughput of storage device. And last but not least, the previous SSD we used to access, file-based access like you do with Linux. With the persistent memory, everything is byte addressable, like Ken mentioned. Now, you may ask yourself how fast we reach. So this is, like Ken mentioned, very, very close to DRAM, but we cannot expose it unless you sign NDA. This is a new technology, I'm sorry. And you may ask yourself, is this technology can be used as a persistent? So yes, 3D Crosspoint is a persistent memory, but if you deploy it in a cloud environment, you cannot use it as a durable persistency, because if the nodes that you're using fails, you're going to be running your application on a different node that the cloud provider launched for you, and you're not going to be able to access the information that you store in this technology. So this is a persistent technology. If you restart the server and you keep the same instance, this runs okay. But if failover happens, you're going to lose your entire data. So you need to add a different layer for data persistence. This is very important because if you think how this 3D Crosspoint technology is going to change the world of the database. So let's say in 2 years, 3 years from now, you will have multi-terabyte at affordable price with byte access to the memory. You don't need to do any disk processing anymore. Everything can be done with RAM at the same price like it is today with SSD. The only reason for you to keep persistent storage is for recovery purposes, yeah? And for that, you can simplify the persistent storage, yeah? You can just add your changes. You don't need to use bit trees. You don't need to use anything else. Everything that you need for this persistent storage is in case that everything fails, you need to be able to recover. You are going to use a fast network in order to scale or to provide high availability with your replica. And let me ask you, do you think you know a database that was designed like this? Do you have something in mind? Okay. The answer, of course, is Redis, yeah? That was designed 10 years ago for a technology that is going to conquer the world in just a few years from now. And I think this is very impressive for the Redis user who chooses to use with Redis. This practically means that you are safe. This is the way to go. Other databases will have to change the architecture completely in order to fully utilize this type of technology. By the way, Redis on Flash on SSD is now available as a fully managed service, or you can download the software and try it yourself. And there are a few, like Ken mentioned, there are a few sessions today which are very interesting. One is at 1 p.m. by Andy from Intel. He will give you all the bits and bytes behind this wonderful technology. And the other one is by Ethermax, a customer of us, who switched their entire Redis on RAM experience to Redis on Flash and use it as a primary database. And before I complete my session, I would like to invite Ofer to give the final notes.